and I thought it would make it a little bit more exciting, possibly. So, as I said, my name is Diogo Montalvão. I'm also head of the Department of Design Engineering and an associate professor in structural dynamics. I'm a mechanical engineer. I also have here with me Dr. Sina Safari, who is a postdoctoral research assistant in structural dynamics and advanced materials, and he's going to present some of the slides as he has been working with me on this project, which is the ADDISONIC. So I'm going to introduce that, but I'm also going to talk first a little bit about myself. So the question I'll try to answer today, with some technical content, obviously, is what inspired us to pursue ultrasonic fatigue testing, and how does it improve aircraft sustainable component design, safety, and performance? So a little bit about me first. I think it's important that you know who I am. So my name is Diogo Montalvão, as I said, and I work for Bournemouth University. I am going to just change here the pointer to a laser pointer to help me a bit navigating the slides, as I don't have the engagement with them as in a face-to-face session. I'm a fellow of the Institution of Mechanical Engineers and a fellow of the Institution of Engineering Designers. And I started my career in Portugal in a small company called Joca. No one knows what it is, probably. And I started there as a draftsman. I did engineering drawings, technical engineering drawings for hydraulic lifts, basically. Then I went to ADDITRANS, which was bought by Bombardier Transportation, but I was working in the rolling stock industry. So it basically in maintenance of rail vehicles, reliability-centered maintenance of rail vehicles. I was then invited to go to academia from a polytechnic, a small polytechnic in Portugal. And it was great because that gave me access to something that I'm quite passionate about, which is airplanes. I did lots of consultancy work to aeronautical industry, and I'm going to show in the next slide some of the stuff I did by then when I was in the Polytechnic. Eventually, I did a PhD in the University of Lisbon, so this is Technical Lisboa, and I became an assistant professor in the MIT Portugal doctoral program in engineering design and advanced manufacturing. I then progressed to the University of Hertfordshire in the UK in 2012, and I'm in Bournemouth University since 2016. I have here my expertise. Basically, there are three core areas I'd like to highlight, which is dynamics, structural dynamics, vibration analysis, model analysis, material science, because we use materials to make our structures, and that's quite an important part of it. We wouldn't have structures without materials. And I like to analyze data, and I also like coding. So that's basically where I'd say my expertise sits. This is now just a little bit more about me, some of the projects I was involved with, and they pretty much all relate to experimental model analysis. I'm going to explain what model analysis is in a second. I'm not sure what the backgrounds are of those attending, but if I start here on the bottom left corner, this was work that I did during my master's project to develop a sensor to measure rotational vibrations. And then I did my PhD in structural health monitoring of composite laminates using a scanning laser Doppler vibrometer. So these are these plates on the bottom actually are scraped material from OGMA, which is the Portuguese aeronautical industries. So I got material from there and also prepared to make my own specimens for testing. But we were basically testing plates and trying to locate the damage from barely visible impact damage from, for example, a bird strike or hailstones that would otherwise not be visible from the outside using vibration signals. This here on the top left corner is a little contribution I had to the intermediate experimental vehicle which is an European space vehicle, experimental European space vehicle in a project for Thales Alenia Space. And we were basically doing the dynamic characterization of some CMC or carbon matrix carbon components, which are used for the heat re-entry of the spaceship. And this one on the top right corner was about structural modification of a C-130 Lockheed Martin aircraft for electronic war, basically. And we had some vibration problems. And so I acquired data in flight. So it was quite an exciting project for me because I'm a mechanical engineer. So I don't often have the opportunity to fly real airplanes. So I flew quite a few times in this aircraft to acquire vibration signals and fix a problem here on aerodynamics on the SAP door, which is the access to the fuel compartment. So that door was basically disappearing in flight. So a few basic definitions. Now, I would like to apologize in advance if this is not real news for you, but I thought that this presentation was meant to be for everyone. I'm not sure what the expertise is of people in the audience. So I thought that it wouldn't hurt if I would just go briefly through very basic definitions before I would crack on with ultrasonic fatigue testing. So the first thing I want to talk about, so it's basically just two definitions, is what mode shapes are without going into mathematical content, obviously. So for those who are more familiar with, they would know that they are eigenvectors. But if we look here to this mass spring system, we have two mode shapes. So we have one mode shape on the left and one other mode shape on the right. All structures have mode shapes, they are infinite. And as you can see as well, the rate of change of the displacement or the velocity or so the frequency, that's what I'm trying to talk about per unit time, is different. So as the mode shape becomes more complex or complicated, the frequency increases. And the frequency attached to the mode shape, which is the eigenvalues, includes information about the natural frequency. So this is important to know, mode shapes. Here we have on the right some simulations and experiments on plates. I used to conduct this to show students about mode shapes. These are actual photos that I took myself. Basically, we excite at a resonant frequency and we spread sand on the plate and it will sit on what we call nodal lines. And we get these amazing pictures. And these are simulations that show the mode shapes. Now, these mode shapes are important because the difference between the system on the left and on the right is that on the left, we've got lumped mass system. So it's a discrete model, whereas on the right, we've got a continuous, a solid model. In this case, it's shell. And this is important because, as you can see at the bottom, from videos I took from the internet, they aren't mine, most of the three of them on the right, on the three bottom ones, so the first, second, and third, are in wind tunnels. They show a phenomenon called actually flutter. It's not real a resonance phenomenon, but it's quite closely related. And we can see how this can have an impact on aircraft. And because of fatigue, which is what's happening here, eventually this will bring structural damage. This one here on the right is the Volgograd Bridge, which is very easy to see. I had videos also of the Millennium Bridge in London, which you probably read on the news, but it's not so easy to see the deformation. Therefore, I didn't really include it in the slides today. And then there is the Tacoma Narrows Bridge that you are probably all familiar with, where the bridge behaves like the wing of an airplane and is subjected to fluid structure interaction that eventually leads to collapse. So this is mode shapes. And then on the next one, I've got a video of myself, which is quite embarrassing. Is it going to work? Why is it not? Is it because of the pointer? Let me see if I remove the pointer as a pointer. Let's see what it shows. So basically on that video, I am going to apply cyclic loading to a paper clip. So you all know this as well. But for those who are not familiar with the subject, for example, if you were from a background in telecommunications or electronics, that could be the case, then you might not know what fatigue is. This is fatigue. This is low cycle fatigue, what I just showed. It's in the plastic domain, but still is fatigue. And the information about fatigue is important because, for example, of program obsolescence. So we have here a light bulb. We all know that what a light bulb is, but they are designed to last, for example, 25,000 hours or a certain number of on-off clicks. It will then eventually fail after that amount of hours of operation. So that's what fatigue is, and we use this information to design products for life. So now that we are off with the basic definitions, and again, apologies about if they were too basic, let's go to introduction to the topic. So the first thing is, I will apologize in advance again if I'm using these acronyms as if they are truly existing words. So we have two of them that I might use quite a lot, but I'll try to avoid them, which is VHCF, means very high cycle fatigue, and UFT, which means ultrasonic fatigue testing. And the two are quite closely related because it's very difficult for us to test up to very high cycle fatigue regime if we don't have ultrasonic fatigue testing. And ultrasonic fatigue testing is actually has limitations as well as every method. It's not very good for low cycle fatigue. It's good for high cycle or very high cycle fatigue. So they are closely linked together. So why do we need this? So what we know is that with the development that we've been experiencing over the last century, and this as well, new equipment expect to have increased lifetimes. There are also increased safety requirements for qualification, for example, in mechanical components. There is expectation also that products last longer than they used to, for example, because of the environment, so that they are more sustainable. And we need to know the damage mechanics and fracture mechanisms so that we can actually understand what is the lifespan of our components and what are the actions we can take to increase the reliability or if its lifespan. We have here examples from obviously evolution of trains and how the speed increased over the years. And this is the new maglev with the maximum speed of they are trying to reach 1,000 kilometers per hour. So talking about maybe 640 miles per hour. So that's quite significant. So it's the same as an aircraft. And then we have obviously Elon Musk's a bit megalomaniac, maybe not, but maybe yes, ideas of trying to launch space rockets to spacecrafts to travel from New York to London, for example, in just 29 minutes. So this will be a lot more demanding to structures, and we'll have, obviously, because of increase of speed, increase also of the frequencies involved in the way that the loads change in a structure. So the other thing that we now know is that because of that, materials now need to be studied at the very high cycle fatigue domain. So what is that? So we have here a plot, and this plot is stress on the vertical axis versus the number of cycles to failure. So if, for those who aren't familiar with the topic, if you measure the paper clip, that's when I do, each time I repeat this motion, that's the one cycle. So when I repeat 1, 2, 3, so I count the number of cycles until it breaks. And as it is obvious, the higher the stress amplitude, the lower the number of the stresses is. Oh, sorry about this. I'm trying to, yes. So the higher the stress, the lower the number of cycles. Now, we've got here several stages. On the left, we have what is called the low cycle fatigue regime. In the middle, we have what is called the high cycle fatigue regime. And then we've got what is called the very high cycle fatigue regime. In the past, we used to say that there was an endurance limit. And when designing, if you know the books from, I don't know, from Peter Childs or from Shigley, they would probably speak about, okay, when I'm designing for fatigue, for life, from 10 to the power 6 or 10 to the power 7, we consider there is infinite life. However, that's an approximation, obviously, and then we have all the factors of safety and and the correction factors on the design. But the point is that there is no such thing, and that is now known as a fatigue limit. So there is no such thing as infinite life. So it's important to test above a certain number of cycles. But that brings problems, which is the time taken to complete a single test, which I'm going to show later. I also got here this is actually from the automotive sector, and I'm noticing now the word automotive, which is a bit annoying, but what I wanted to highlight is that within the industry, the ultimate goal is to add very high cycle fatigue tests to the current LCF, which means low cycle fatigue, / HCF, high cycle fatigue testing, which will more accurately predict long-term fatigue life within the automotive sector and obviously other sectors as well. So basically what we want to do is to include this in the mix of the testing we already use. Other things that are interesting, and this was a PhD student I had, an excellent PhD student I actually had, and he was working with other colleagues in a very exciting project, which was on electromagnetic treatments on different metal alloys, including aluminium and nickel titanium as well. And what he found out was that we can improve some or enhance some properties, namely resistance to cavitation erosion, resistance to wear, so the hardness. And here we are comparing two materials, nickel, aluminium, bronze, and a 2014 T6 aluminium alloy. And also there were hints that we could, with these treatments, we could improve the fatigue lifetime, even when the parts are being serviced, so are after service. So they were operating, we apply the treatment, and then that brings back the lifetime. If we think in reliability terms, it's like reducing the failure rate, so the chances to fail. Now, the problem was that we couldn't really determine that because there was just no time. It wasn't feasible to do the tests in a lab because there was just time. A single specimen could take months to complete. So the ultrasonic fatigue testing will respond to that because it's accelerated testing. The other importance of doing fatigue testing and accelerated is that there is a need for predictability of material properties that we didn't know before. So on additive manufacturing, for example, we can't just go to a table or to the supplier of material and get the data because it just doesn't exist. Then it's just not about the powder that we get, for example, in sintering. It's also about, well, what is the machine I'm using? So that's really critical because we might have voids, for example. The other problem is that the way I print a part is going to be critical because if I part in horizontal layers or vertical layers, then that might change the behavior of the parts. So that the parts that are 3D printed are no longer isotropic. They tend to be anisotropic. If it is a composite material, it could be orthotropic, very likely, and has other challenges as well. So how do we get this data? If we're using traditional methods of testing in a tensile test machine, a universal tensile test machine, for example, it might take a very long time to get those answers. And so to get basically the SN, which is the stress to life or stress to the number of cycles to failure diagrams, as one I just showed earlier, where we could see the infinite life. Then there is a push towards design for sustainability. And this is actually not that new anymore, but this is something that I don't have I should have the reference, but I forgot to put it there. This is from the Professional Engineering magazine from the MEng. So if you keep them, then you might have this article, which is quite interesting. I think this is from 2017 or around that. And basically, General Electric unveiled its turbopropeller demonstrated power plants. And this is it uses more 3D printed parts than any other engine in history. So basically, they managed to replace 855 traditional tool parts with 12 printed ones. So I don't know what developments are from this publication, but this is quite an exciting development, and obviously demonstrates and showcases what the future awaits. So what is ultrasonic fatigue testing after all? So contrary to normal fatigue testing, normal conventional, where you use a rotating fatigue machine, so we basically, but we need to clamp it in both locations, or universal testing machine, where we apply tensile or compressive force. This one is a bit different. We use an actuator, which is actually something that is used for welding, and we have then what is called a booster. So this is a piezoelectric actuator here, which is vibrating at a certain frequency. Then we have a booster that amplifies the vibration. Then we have a horn, which is another amplification of the vibration. The difference is that the booster has here, this ring here is a support, which is a node of vibration. As you can see there, it doesn't move. And then we've got the specimen to test. In this case, this is uniaxial. But this is all based on reproducing free vibration working in natural frequency. So all these components are vibrating at their natural frequency. So they are all designed to vibrate in natural frequency. And the connection points, like that one between the horn and the booster, and between the horn and the specimen, they are vibrating in free approximated conditions. So that's the principle behind ultrasonic fatigue testing. And what is exciting about that is that the mode shape generates the deformation, that generates the stress at the location that we want to excite, and we only need one actuator, which is quite an interesting aspect of this type of testing. The frequencies that we usually use are 20 kilohertz. There is a reason for that, is that the noise can be quite annoying. So if we go for frequencies below 20 kilohertz, we will hear it. Even myself, my hearing is now probably a bit damaged up to 17, 18 kilohertz. Above that, I don't hear a thing. But if we go below, it might be quite annoying or upsetting and disturbing. If we go above, then we have problems with scalability of the specimens. So 20 kilohertz has been accepted as the standard frequency, and that's why it's 20 kilohertz. This is the control diagram. This is the first machine I developed, which is in the University of Lisbon, or I helped developing. It was not just myself. I did all the control of that machine, where you can see that the piezoelectric actuator, specimen over there, an infrared thermometer. We were using some fans to cool down the specimen. And then we used, this was quite a cheap National Instruments data acquisition and control device. So we get the temperature displacement measurement from a laser. That's a Polytech laser Doppler vibrometer. And we then do the control in LabVIEW. And we can also obtain thermographic images. And this is used to tell us that if the temperature is increasing, then that's a sign that the stress is increasing as well. This technique generates a lot of heat, which is one of the downsides. But one of the advantages is that if we compare, say, an ultrasonic, an universal hydraulic test machine from Instron, that typically works between 1 to 50 hertz, and ultrasonic fatigue testing machine that works at 20 kilohertz, and you can see you don't have anything on this end, whereas here you need 2 clamps. And if we do the math, and if we consider 30 hertz, in this case I placed a rotating bending, but could be anything, compared to 20 kilohertz, to reach very high cycle fatigue regime, it takes us, in theory, half a day on ultrasonic fatigue testing machine, and 1 year in rotating bending at 30 hertz for a single specimen working 24/7. This is not exactly true for the ultrasonic because of the heating. We need to stop. So it might take us a few days, maybe 3 or 4 days until we get the crack. But it still is a great improvement compared to a conventional test method. And if we wanted to reach 10 to the power of 10 cycles, it would take us 1 week on 30 hertz, working 24/7 non-stop. That would be 10 years, basically, what we would get, because it's tenfolded the number of cycles. So this kind of opens us an opportunity to get data for very high cycle fatigue regime. Or if you want to look at it in another way, if you, okay, I'm not interested in 10 to the power of 9, I'm interested in 10 to the power of 8 number of cycles, well, we can do that in just a couple of hours compared to months in a rotating bending at 30 hertz. So you can get very quickly data in our testing. Below 10 to the power 6, we don't want to use ultrasonic fatigue testing machine, but then the conventional test methods are already giving us reasonable times to get the data. So that's fine. So this is useful for quick predictability at high cycle fatigue, very high cycle fatigue. There are some challenges, I think. CEng is going to talk about them. One of them is strain rate. You might be already thinking about that. Some materials are frequency dependent. I think he's going to touch base on that. Temperature control, I already mentioned that, and it also has an effect in the behavior of the materials. So the problem is, because of damping, when we start the measurement, the temperature will increase. So we need to stop. We need to specify an upper limit, and then we need to cool down the specimen and then start again and stop and so on and so forth. So it's not continuous. This also brings other questions that could be, well, will that have an influence in the results? Because we all know that when we turn on and off something from control systems, we all know that there is an overshoot. Well, it's a price to pay for the technique. So obviously there are limitations. We don't want to hide them. Data acquisition, that's no longer really a limitation or challenge. I left it there because this technique exists since the 60s. However, because in the 60s there was no capacity to acquire data, it kind of was waiting for data acquisition technology to evolve. And so from the last 10 years, 20 years, this is when the community start getting an interest in ultrasonic fatigue testing. Low cycle fatigue, well, that's a challenge, but we can do it in conventional testing. That's not a problem. Scalability as well, and how it compares, because of frequency-dependent materials, with normal testing. And this is taken from a paper where they could see that there were some differences between the SN curves obtained in ultrasonic fatigue testing and obtained in rotary bending. But there are ways of calibrating the two curves, and from the ultrasonic data, convert it into the equivalent to lower speed version. So that's something that is interesting to know. And some materials are more frequency dependent than others. So these differences might be more exacerbated in certain materials than others. Just to notice that I have here a close-up of our machine. So we measure the temperature with an infrared thermometer, and we have a vortex cooling machine, which is basically connected to a compressed air, and compressed air comes in here tangentially. It will then create a vortex. It will spin, go to the outlet on the right, but only a certain portion of air is allowed to go out. So what's going to happen is that some air is going to push in, which goes inside. So there will be exchange of changing pressure and also exchange of temperatures. So on the right, there will be heat being generated, and on the left, cold air being generated. Obviously, the balance will be the room temperature. And this is a laser that measures the displacement at the tip of the specimen so that we can relate it to this stress at the center. But we've got digital image correlation, which CEng is going to talk about, that allows us to measure at very high speed the actual stress that we have getting in the specimen. Other advantages of ultrasonic fatigue testing is that it is highly versatile. Because it is model-based, we can do multi-axial testing with a single actuator as long as the specimen is designed to allow us that. This is an in-plane biaxial specimen. I claim to be the first person to in the world to basically tune a specimen that exists. So I picked up a specimen that existed on conventional testing, and I tuned it to use it in a ultrasonic fatigue testing machine. And we can do loads of stuff with the same machine. We can have in-phase or pure, equibiaxial testing. We can have out-of-phase mode shape. So when this arm is in compression, that's in tension and vice versa, which is basically pure shear. So we are here. And we can also get different biaxiality ratios, which is what we're showing there on that picture. So I thought it would be interesting for me to talk a little bit about biaxial fatigue so that I can explain what this is. This is relevant because multi-axial stresses are actually what is occurring in real structure. There is no such, well, this is not true. We might have uniaxial stress. Even a uniaxial specimen, the specimen, if you think about that, because of the Poisson ratio, is biaxial. So if I have steel, for example, I will always get, in a uniaxial specimen, if I have the stress in one direction, that is, say, 10, the stress in the other direction will be around about 3 megapascal or whatever unit is. So biaxial stresses are really what are happening in real life. And this includes components, critical components used in many industries. And here I've got examples that I got from elsewhere. I've got there the link. And we have many different examples where this could be critical, and especially, for example, in turbine blades and in nuclear generators and even in fusion reactors as well. So this could be quite relevant. So a lot of researchers have been focusing on testing cruciform specimens. And here we have examples that I got from the literature. This one here on an FEA model, and then these two machines here on the right. And we can see they are quite complicated machines. They need to be very well synchronized, and they are just complicated. I know the team who made this machine here. This was quite a clever design, and the actuators are sitting on air beds with compressed air so that they minimize friction and can ensure that they've got a reliable reading of the loads. And then we have different types of specimens here in the middle. Now, the problem with that is complexity, but with the ultrasonic fatigue testing machine, the same that is used for uniaxial specimens, we can still do the biaxial ones as well. So here we've got cruciform specimens. Again, the same picture I showed you earlier. And here the machine, or schematic of the machine, again, piezoelectric actuator at the top, the booster, the horn, and then the specimen. But because the specimen is connected through an antinode of vibration of that particular mode shape, it will vibrate with that mode shape. If you know about vibration theory, then this should make sense to you. So the coupling is at the correct coordinates, and so I will get the mode shape that I have designed for, as long as this is an antinode of vibration. We can change the arm's length, by the way, and get different biaxiality ratios between the two axes. And the good thing is that only one actuator is needed. That's it. So, actually, I'll need to stop sharing, and I will share right because I forgot to do something. And Jenny reminded me of that, and I forgot, obviously, which is when I want to share sounds, I need to tick a box here that says share sound. So let's see. So, okay. So here we are. So what I've got now is basically, I have here a specimen, and I'm going to basically hear to its sound by holding it at a node of vibration, which is actually the center. Let's see if we can hear it. So you can hear there are many different harmonics happening, but the important one I wanted to highlight is that one over there, which in this case is around about 20,110 hertz. So the specimen was designed in a computer using finite element analysis, obviously. Then we made it using subtractive manufacturing in a CNC machine. This one, in this case, this is aluminum, and we tested it to check if it was resonating at 20 kilohertz, and then we can place it in the machine safely and test it to fatigue. There are obviously some problems, and here is a specimen that didn't work really well, and we had heating being generated at the top. We had some problems with the mode shapes, and here we have a spurious peak over there. So we need to make some adjustments to the design of the specimens because we want to have a pure harmonic signal. And once that's done, we can see that we're getting good data. The maximum stress is at the center. And in this case, the fracture was around about 45 degrees, which in this case, this is a pure shear specimen, is exactly what we expect to get from theory. These are just simulations illustrating how cruciform specimens with non-unitary biaxiality ratios would deform. So actually, first one is equibiaxial. So you have basically the same stress in both directions. The second one is pure shear. So the arms are deforming out of phase. The third one has a biaxiality ratio that is positive, meaning that the stress in both directions is either positive or negative during the motion. And the fourth one is when the biaxiality ratio is smaller than 0, so it's negative. So one of the directions is positive, the other one is negative, and vice versa. So again, this is basically, I showed this earlier, so this is maybe a repetition of the two stresses. And in this case that we've got here, we would get somewhere over there. That's more or less what we've got over there. Okay, right. This is another type of biaxial fatigue that we can get. In this case, I'm not going to develop much into this in this presentation. I think this is the only slide I'm showing. But we had to change the horn. This is a bit more complicated. This horn actually is patented, and it has been patented and has some special features. So what's happening in this case is that the horn and the specimen are both stretching and twisting at the same time. So there is tension and torsion or twisting at the same time. This is more complicated in terms of design than the previous one. I don't want to bore you to death with that. The other one was a single mode, so the mode shape does everything for you. In this case, we have two mode shapes that have to be tuned to have the same frequency. So it's a lot more challenging, the design on this one. But it has interesting applications, like could be gears, like bevel gears, or springs, helical springs. So there are many different types of applications where this could be interesting also to test. So we reached now to the stage where we're going to talk a little bit about the calibration of our ultrasonic fatigue testing machine at Bournemouth University in the ADDISONIC. And CEng, this is where you can say a few words and let me know when to change the slides.
All right. Hello, everyone. My name is CEng Safari. I'm a postdoctoral researcher working with Diogo in this interesting project in the ADDISONIC research cluster. I'm going to just briefly describe how we are doing the test in the lab and how we collect the data and process them. So this just shows some snapshots of what equipment we are using. We have like data acquisition system, as Diogo showed. We have lasers, like the temperature measurement, cooling system, and the specimen connected to the machine. And also we have this nice camera which is recording the images of the vibration. And this big one actually is working in the 125 kHz. So we can have very quick images snapped. So the other one is showing the connections actually we have. For example, the booster connection, which is actually, as Diogo mentioned, is the node point. So we can connect it somewhere without like disturbing the intended mode shape. And as you can see, there is altered connection. And these are sometimes making one of the challenges actually these days we are like facing is bolted connection. Always there is friction, and they induce some different maybe mode shapes, and we try to to kind of control them to achieve what we need. Basically, in that high frequency, if we have friction, which is a nonlinearity, it can cause some mold shapes. But yeah, we could kind of control them properly to do the tests. So yeah, this is the setup we have in the lab, and actually, I'm in the same lab at the moment. In this slide, I'm going to talk about some standard procedure to do the calibration of the machine and how we can extract the data. At the moment, I think there is one standard, Japanese standard, which is very, very brief and kind of first one in the world, talking about the ultrasonic fatigue testing, specifically on metallic materials at the moment. So there are a couple of steps to go on with. First of all, we need to see and calibrate and validate the laser leading at the tip of the specimen. And then we should also calibrate and validate if the DIC system, digital image correlation system, is working. After we make sure that they are showing the correct results, we need to make sure that the intended mold shape is excited, which means, as you can see in this animation here, we need to make sure that the top plate of the specimen and the one down there, they are working synchronously and they are working as designed, intended. So we can put another laser, or we can use the DIC system to just observe the vibration mode, and we can make sure it's exactly what's happening in the simulation. It's happening in the physical world. So that's the second step. In the third step, we can build a statistical relationship between the strain measured. What I mean by strain, we have like this knee in the middle of the specimen, which we measure, where we measure actually the strain using the DIC system. And then using the laser, we measure the tip displacement. So there is a relationship, because the specimen, we are assuming it's in the linear regime. There is a linear relationship between the tip displacement and the strain in the middle of the specimen. So that's one of the steps that we need to carry out to find out the relationship between the laser reading at the tip of the specimen and the strain in the middle section of the specimen. At least we need 5 points that I'm going to show in the next slide, hopefully, to do this process that could be measured throughout the capacity range of the testing machine. And then finally, we need to always control the surface temperature in the high stress part of the specimen. And as it is specified by the Japanese standard, it should be lower than 30 centigrade. It's just a guideline. So sometimes, you know, we can kind of go over it, or depends on the material as well. So this figure here is just showing how the test is working. Like we just excite the machine. It starts vibrating in 20 kHz. Then the cooling system starts and the machine stops vibrating. As you can see, we have like very quick pre-decay response, and the vibration dies down and the cooling system works, and then after cooling it just starts again. So in the next slide I'm going to show how the cooling system is working in practice in our lab. So as you can see again in this figure, during the vibration, the figure below shows that the temperature is rising, and then when the vibration stops, the cooling system just cools down the specimen to a certain level. We can specify a higher threshold than low threshold, so the cooling system can identify them when to stop and when to stop. And this is what's happening exactly. So actually, we can use this data smartly and just count the number of cycles. As you can see, those gray areas are the vibrating areas, or the time of vibration. So if we know the vibration frequency, let's say if it's 20K, hertz, we can just multiply it with the number of seconds, and that's going to give us the number of cycles. So from the temperature also we can calculate the number of cycles. That might not be quite reliable, but it's kind of a like good approximation. We have like real-time counting system here in the controlled part of the testing machine that counts the number of cycles for us. So yes. So in the next slide, we move on. Thank you. So this slide shows exactly how we measure the strain in the middle section of the specimen using the DIC system. So if we play that and also play the one in the bottom, so as you can see, we have the simulation of vibration, and that shows the stress in the middle, or strain. Yeah, it should be. Both of them are similar. We can because it's in the linear regime. So it shows the strain, for example, in the middle of the specimen using simulation, and what we are observing in the experiment using the DIC system, and the wave down there, the cyclic motion down there, shows us the strain in the middle section. So this is like how we use the simulation and experimental data to calibrate, to make sure if the machine is working as designed, and also to calibrate the FE model based on what we are observing in the experiment for later stages. So if we move on to the next slide. So this slide is about how we kind of build that relationship between the tip displacement and the strain in the middle, which we can calculate the stress from. Because there are some uncertainties involved. As you can see, I collected in this figure, I collected some data points for different displacements at the tip in the figure in the top right. So those data points, for example, just below 5 micrometer, I excite the system, I measure the tip displacement using laser, and using the camera, I measure the strain. So I repeat this process many times and collected many data for each tip displacement, or let's say operational level of the machine. So if we collect those data for different tip displacement, it can give me the strain for each those operational level, and then I can kind of build a relationship between the tip displacement and the strain. The first thing to notice is it's pretty linear, as you can see, that the data shows a pretty linear trend. And what we can propose is easily just say, okay, I have a linear relationship as a model, which shows the strain is correlated with the displacement. So we used a hierarchy of Bayesian inference. I'm not going to elaborate too much on the algorithm there, but it just means that if you have multiple data sets, not just one data set, you can use like a hierarchy of a regression to find out the uncertainty in the data and distribute it. So that's the whole process about that. So when we built that relationship, now we have the tip displacement and strain. Now we can go and find out the number of cycles for that strain or stress level. Right? So for example, I'm going to excite this structure or the machine at the tip displacement 10 micron. That represents, based on this bottom left graph, that represents, for example, a strain higher than 1,000 micrometer, and then I can build actually the relationship between the strain and also this number of cycles. So these are the data points based on recommendation. 12 specimen we just broke for the very high cycle regime, and we had some data for low cycle regime as well. So as you can see, we can feed these data again using regression or a simple model, and we can find out the trend with some confidence interval. And just take this into account that this very high cycle fatigue regime with normal machines will take, as Diogo mentioned, up to 1 billion cycles. It will take 1 year to do just one specimen. But with this machine, it's just achievable in a big, just 12 specimen. We can find out these data points and build this stress cycle, number cycle curve. Okay. So if we move on to the next slide, this is again showing different fitting methods for different fitting model, different model we can use. In the very high cycle fatigue regime, I use the linear model, or I put the whole data together and use the nonlinear model. And there is a reason for this, because there are some literature that propose that if we continue the regime we are observing in the low cycle to the high cycle and very high cycle, we will get good estimation of the CEng curve actually. So this graph here shows 3 regimes. Regime 1, which is low cycle fatigue, and as you can see in the regime 1 we have like elastoplastic behavior, and we can say there is dominant plasticity there. In the second regime, where we have like transition between low to high cycle regime, we have a little bit plasticity involved in the macrostructure. And in the third regime, which is very high cycle fatigue regime, the system is almost linear. So the question where the damage is coming from actually, that comes from the microstructure. So what is actually governing the damage in very high cycle regime, I would like to answer is the microstructure. So if there is a very small microstructure defect, or after many cycles, if there is a microplasticity in some region of the structure, it's starting to develop. So here in this regime, in the very high cycle fatigue regime, the microstructure is very important, and this is one of the challenges actually that should be addressed. Okay, I think that was my part, Diego.
Thank you very much, Sina. I'm conscious of time. I need to now speed up a little bit. So yeah, you already covered most of the stuff in terms of fracture. I'm not going to go into details. These are results I've got from the past, from tests we did in copper, and we can see here the typical beach marks in fatigue in a uniaxial specimen, and the crack developed from a surface defect. However, when we got steel, and this comes back to what Sina was just saying about the microstructure, in steel at very high cycle fatigue regime, the crack nucleates, so develops from many times inclusions or defects inside instead of surface scratches, in what we call a fisheye pattern here, and this is the case, very typical to happen in a steel specimen. But you can still see that the data is comparable on the carbon steel specimen. In biaxial fatigue, not going into much detail, for those who know about fracture, there are 3 types of modes in fracture mechanics. And what we can see is when we have the equibiaxial, so when we are stretching from 2 orthogonal directions, we have mode 1 striations, means that we're getting opening as expected, although the angle wasn't really, so we can say they're at the center, so that's the angle. We can see it very well. That's where it is. It's 53 degrees, not too bad. We're looking for 45 degrees. In the pure shear, we got 40 degrees on the center of the fracture, and we have shear marks, which is the mode 2, as expected, and then there is a bifurcation, which has been observed by other researchers before in aluminium. So just to finalize a bit about the ADDISONIC Research Cluster, it's funded by Research England with at the moment 265,000 plus pounds, and has a mission to contribute to reducing global waste, enhance the optimization of engineering systems by helping engineers incorporating advanced materials which are tested under ultrasonic fatigue for quick and reliable predictability of properties to extend their lives and enhance design for manufacturing. These videos are just, it's 3D printing at university of metals and carbon fiber specimens as well. So I had here a video. I'm not sure this is going to, yeah, I'm conscious of time. I'm going to probably skip this. This was just to show the digital image correlation showing the deformation of the specimen, and that's the camera over there, and then comparing with the finite element model. And oh, actually, it's now running. And this wasn't intended. This was a specimen with a problem, but what we can see is that the specimen did have the, it's not, we can't see anything, but the camera is picking up, and this is the simulation, and we are trying to determine what the issue was with the mode shape. So, concluding remarks, we need new technologies for the qualification of aeronautical parts and predict how long they will last. This is critical. We are still not at the TRL that we could do that when we are in university. So TRL means technology readiness level, but obviously industries would feel free to explore that. We are looking into ways to reduce waste and extend the lifespan of products, and ultrasonic fatigue testing is helping that, combined with, for example, the electromagnetic treatments that I showed earlier. It's very versatile because we can test different stresses, combination of stresses, and it will help in optimization of the design, on the design of parts. We can test materials over 1 billion cycles in just a few days, and it can help reduce global waste, and I mentioned that already, so it's a repetition, and improve product performance in various industries because it gives us loads of data in a very quick fashion. So that's it, basically. I kind of managed to, I think, meet the 8:30 time. So that's it. I don't know if you have any questions. I would be more than happy to try and answer them. If they are too hard, I'm not sure if I'll be able to, but thank you very much for watching.
Thank you very much, Diogo. I'm going to stop the recording and then we can ask questions. I will try to ask questions.